Hello, I'm Trent Parado, Public Affairs Officer for NASA's Science Mission Directorate in Washington, D.C. I'd like to welcome you all today to the news conference to discuss the latest findings from the NASA's Kepler mission. Kepler is the first NASA mission capable of finding Earth-sized planets in or near the habitable zone. That's the region in a planetary system where liquid water could exist on the surface of an orbiting planet. Additionally, Kepler is detecting planets and planet candidates with a wide range of sizes and orbital distances to help us better understand our place in the galaxy. For those joining us online, you can find out more information at www.nasa.gov/Kepler. As for the order of events today, we have 4 panelists joining us. Each will give a short briefing, and then we'll open the floor and the phone lines for questions and answers. I'd like to take a brief moment to welcome and introduce the panelists. First, we have Douglas Hudgens, Kepler Program Scientist, NASA Headquarters in Washington. Next, Bill Barucki, Kepler Science Principal Investigator in NASA's Ames Research Center at Moffett Field, California. Jack Lissauer, Kepler Co-Investigator and Planetary Scientist at Ames. And Deborah Fisher, Professor of Astronomy at Yale University in New Haven, Connecticut. And with that, I'll hand off the discussion to Doug Hudgens.
Thank you, Trent. Hello there. On behalf of the Astrophysics Division and the Kepler Mission, I'd like to welcome everyone here as we mark the second major public release of data from the Kepler Mission and also announce the discovery of a fascinating new planetary system with more transiting exoplanets than any other system discovered before, all clustered around their star in orbits smaller than the orbit of the planet Venus. As you know, Kepler is NASA's first space telescope dedicated to the search for planets around other stars, also called extrasolar planets or simply exoplanets. That means that the milestones that Kepler achieves with each and every discovery shape the course of all future exoplanet missions. Kepler has been in operation for a little over a year and a half now, continuously monitoring the brightness of more than 150,000 stars in a single patch of sky near the constellation of Cygnus, the Swan. Now, we all know that the holy grail of the Kepler mission is the discovery of an Earth-sized planet orbiting in the habitable zone of a star like our own sun. And believe me, no one is more eager to get to that point than the Kepler team. However, that's going to take time. As I've said, Kepler's only been in operation for about a year and a half, and it'll require at least 3 years of Kepler data, as well as painstaking observations from some of the world's largest ground-based telescopes before those types of planets are going to begin to emerge from the data. However, in the meantime, Kepler is absolutely revolutionizing our understanding of exoplanetary systems and exoplanets of all sizes. Think about it. The first 15 years of exoplanet searches from the ground turned up a little more than 500 extrasolar planets. Last June, the Kepler team announced the discovery of more than 700 extrasolar planet candidates in just the first month and a half of mission data. Today, you're going to hear that when you add the next 3 months of data that were released earlier this morning, the number of candidates jumps to more than 1,200. Now, you might imagine that with more than 1,200 candidates, the key thing is to remember that you'll notice that I talk about exoplanet candidates rather than just exoplanets. And the reason for that is every time we see in the data the evidence of some sort of a signal, that requires analysis and follow-up observations to confirm that that signal is actually due to a planet and not just something masquerading as a planet. Now, you might imagine with more than 1,200 exoplanet candidates at this point, the Kepler science team has been basically trying to drink out of a fire hose to keep up with the follow-on observations. That's why NASA is pleased to be releasing this data at this time and so that it can harness the horsepower of the entire astronomical community. Now, you didn't come here to hear some NASA guy blah, blah, blah endlessly, so I'm going to turn it over to the scientists here pretty soon. But before I do, I simply would like to acknowledge that the results that you're going to hear about today, and in fact all the Kepler results, are the culmination of years of tireless work by scientists, engineers, chief cooks, and bottle washers at NASA Ames Research Center, the Jet Propulsion Laboratory, Ball Aerospace Corporation, and institutions across the country and around the world. The success of the Kepler mission is a tribute to those people's efforts, and I tip my hat to each and every one of them. I'll turn it over to Bill now.
Thank you, Doug. What I'd like to present today is the results of the first 4 months of science operations of the Kepler mission. Doug has and Trent have, I think, well described the mission. Its objective basically is to find Earth-sized planets, particularly in the habitable zone of sun-like stars. Could I have the first figure, please? This is a sketch of the spacecraft itself in orbit looking at a planet transiting a star, and that's how we do our photometry. We look for dimmings of a star. The data that I'm going to talk about is of 155,000 stars that we have been monitoring for 4 months. It's of the 1,235 candidates that we have found, and I will describe those as well. But I'd like to start out first with a family portrait of where we've come from. Could I have the next figure? This basically shows you our confirmed planet discoveries. These aren't candidates, these are confirmed planets. In the first season, we were able to find the top row there, 4 planets bigger than Jupiter, and they're compared to Jupiter there, plus a planet that was about the size of Neptune. That's the green object down in the bottom line. The giant planets were a surprise. We didn't think we would find that many. Certainly the one on your far left was an even bigger surprise. It is a planet with one of the lowest densities ever found. This enormous planet, bigger than Jupiter, has a density of styrofoam. Just astounding. The Neptune was a surprise in that it's extremely close to its star. It's very hot, and you'd think that that would expand it and its density would fall. That is not the case. Another surprise. And this last year, one of the things that we were able to confirm was a star with 3 transiting planets, and that's shown in the bottom row. 2 of these planets, 9b and c, are planets about the size of Saturn, and one of them, that little blue object there, is a planet 1.6 times the size of Earth. So we're down in the super-Earth size. A few weeks ago, the start of 2011, we had another announcement. That is Kepler's first rocky planet, a planet 1.4 to the size of the Earth and a density greater than that of the Earth. So it's obviously a rocky planet of some type. So we're moving into the direction we want, from the bigger, easier planets to the smaller planets that might harbor life. So let's go and talk about not what we had found up to today, but look at the data itself that we released last night. Could I have the next figure, please? When we started out, this was our field of view. It covers 100 square degrees of sky. You see 3 yellow points there. These 3 were planets that were known before we launched. They were in our field of view, and of course made measurements of them. But let's look at the same field of view after looking at 4 months of Kepler data. Next figure, please. This are those 1,200 candidates. We cover the field of view with all sorts of candidates. Let's look at the next figure. We measure the size of these objects. We can tell you which are Earth size, which are Neptune size, which is super Earth size, and you see that in color. The blue dots are Earth-sized planets, Earth-sized candidates, not yet planets. The green ones, the yellow ones, are super Earths, up to twice the size of the Earth, but still planets that, if they're confirmed, might very well have a solid surface people could walk on. Then we have the Neptune, the size, and the giant planet sizes. So a huge range of planets throughout this field of view. Could I have the next figure? This gives you the numbers of what we have found. 68 Earth-sized candidates. Candidates up to 1.25 the size of Earth. Some of these candidates smaller, considerably smaller than the Earth, close to Mars size. Then we have the 288 candidates that are somewhat bigger than the Earth. 662 Neptune-sized candidates. As Doug mentioned earlier, in the 15 years of observations, the total number of known planets that have been discovered is like 520. Just this group alone of candidates exceeds that. So there's an enormous number of candidates that we're finding. 165 Jupiter-sized objects, objects that are even bigger than Jupiter, and we're not quite sure what they are. And so there's 19 of those as well. Let's go to the next figure, please. One of the things that we want to do when we find these candidates is find candidates in particular around stars like the Sun, because there's all sorts of stars out there. Giant stars that have engulfed their planets, various stars that are burned out. We would like to find candidates around stars like our own. And this figure shows that if you look at the Earth-sized candidates and the super-sized and the Neptune-sized, all of those are centered. The maximum number is around the temperature of the star, the temperature of our sun. So these stars are very much like our sun. There's a variety that you see there, but most of them are around stars like the sun. And of course, that didn't happen by accident. It happened because before we launched that mission, our co-investigators, led by Dave Latham at the Smithsonian Astrophysical Observatory, used ground-based telescopes to observe 4.4 million stars in this field of view and classify them. That allowed us to choose just the stars that are most sun-like, and the brightest stars. So we could find really good targets to make these measurements with. The next figure, please. When we look at these candidates, again, I've broken them into 4 groups. The blue group there are Earth-sized, and the green groups super-Earth-sized, and Neptune-sized, and the Jupiter-sized. One of the things we see is the number as a function of the orbital period in days. And you see that each of these curves falls to the right. It gets fewer and fewer as you get to larger and larger orbital periods. This occurs because it's harder to see planets further out. The chance of seeing them is diameter of the star over diameter of the orbit. So as you move further and further out, it gets more and more difficult. So you see fewer and fewer of these candidates and these planets. It gets more difficult as you look for planets toward the habitable zone. The other thing that you notice is there's a peak. The peak here is between 2 and 4 days. And that occurs for every one of the groups. And the thought here is what's happening is that when planets form, they form an accretion disk. And that accretion disk takes momentum and energy from these planets, and they spiral toward their star. And so if they come spiraling in and that orbital period matches the rotation period of the star, tides rise on the star and on the planet such that the star can transfer its rotational momentum to the planet and stop the planet from crashing into the star. And so that's sort of a storage bin of these planets. So we see that very, very clearly in this data. But then you see there's a big dip for periods shorter than 3 or 4 days. And clearly it's easy for us to see short periods planets because they give us so many transits. More transits, the easier to detect them. So this is real. And the implication here is that some of these planets, when they came spiraling in, didn't come in with synchronized with the rotation of the star. And so they continued on their way in and did dissolve into the star. On the other hand, we see some that are still there, and that might mean they were lucky. They simply came in toward the star, and the star lit up, blew away the accretion disk, and now they're safe. Or maybe they're not so safe. They still have tides on those planets, and they may be on their way in to the star yet. So areas of investigation that many scientists will be looking at in the coming months and years. Could I have the next figure, please? When we started out, people had found planets around other stars, and people had found them with a transit technique that we use. And here's an example of the size of the planets they found relative to the Earth. So 1 is Earth size, 4 is Neptune size, and you can see the little sketches of the planets along the edges there. And you see the dots. The dots basically show you that what was being found were planets quite a bit larger than Jupiter and at very short orbital periods. And so we really want to observe not in the upper left corner, but in the lower right corner, where you've got small planets at cool temperatures. So let's look at what Kepler's contributed last June. Next figure, please. you can see all these purple dots, and you can see that most of them are quite a bit smaller than Jupiter. Most of them are the Earth, between Earth size and Neptune size. Further, they're not at the shortest periods, they're at much longer periods. So again, a movement toward the lower right-hand corner. Next figure, please. This is what we released yesterday. This is all the data from those 1,235 candidates, those 150,000 stars shown here. And now you see, again, many more planetary candidates closer to the size of the Earth. And in fact, if you look, a lot of them are below the size of the Earth. These objects are getting down toward Mars size, in fact. So we are seeing smaller candidates. And they're moving to the right to longer orbital periods. You can still see there's a little gap there that we want to go to in the lower right-hand corner. But we ought to talk about the temperatures of these candidates. If they're too hot for life, we want to know that. We want to know their temperatures. Are they cool enough so they could have liquid water on the surface? Could they have an ocean? Could they have an atmosphere? So we're going to change the axes. The horizontal axis is no longer going to be orbital period. It's going to be the temperature that we calculate for the candidates. Could I have the next figure? The temperatures here now are in Fahrenheit. And what we see, again, the size relative to the Earth, we see what we saw before, some smaller than that of the Earth, many between Earth size and Neptune size, and a fair number that are bigger even than Jupiter. The temperatures, 1,000 degrees, twice as hot as a pizza oven. 2,000 degrees, you've got those planets are molten lava. 3,000 degrees, they're molten iron. So very, very hot. The area of interest now is not in the lower right, it's in the lower left. So let's go and expand that lower left. Could I have the next figure, please? So we're going to take this portion of that group of 1,200 candidates and expand that out so that you can see in detail what the temperatures look like for those that are close or in the habitable zone. Next figure, please. This is that expanded area. Now you see the temperatures aren't in thousands, but they're temperatures that many of us experience, from 0 Fahrenheit up to 200 Fahrenheit, and some colder temperatures as well. This is the region where you could have liquid water. Now, clearly, minus 50 Fahrenheit, you don't have liquid water, you have ice. But if you have an atmosphere, those temperatures will come up as well. And so now we're seeing, in the habitable zone of these stars, 54 candidates, one of which you can see is smaller than Earth. 4 of them are somewhat larger than Earth. They're super-Earth size. We see many in the Jupiter, the Neptune, the Jupiter, and some greater than Jupiter. Now that's rather interesting. Jupiter's big enough, mass enough, so you could have Earth-like moons orbiting Jupiter. If that Jupiter's in the habitable zone. So those moons are also in the habitable zone. All the moons of Jupiter, those Jupiters, are in the habitable zone. And you can imagine some of them, if they were Earth-sized, could have atmospheres. They're close to one another, so for your Christmas vacation, you could go from one moon to another and have a vacation on a different moon. So I'm not saying that happens every day, but it's conceivable. So lots of habitable zone candidates here for us to follow up. Clearly, it's some area that we will be working very hard in the next months and years to confirm. Next figure, please. One of the great things that happened earlier this year was the confirmation of Kepler's first rocky planet. This rocky planet is 1.4 times the size of the Earth. We were able to confirm it. We were able to photometrically detect it, get the period, get the epoch, but you want to confirm it. You want some other method to prove this is indeed a planet. And the radial velocity work here, rather heroic work by a number of team members at Keck and many other observatories, HET, Nordic Optical Telescope, the Wind Telescope, allowed us to confirm this as a rocky planet, get a density. But as we talk about these small planets, the planets we're most interested in, the signal for radial velocity is very small. It takes a lot of time. And this is in an orbital period of less than 1 day. Its year is less than 1 day. And so that signal is still fairly large. But as we move further out into larger orbital periods, 30 days, 50 days, 300 days, the signal gets so small, we probably will not be able to do that for many, if any, of these small rocky planets. Instead, we need a method that supplements it. Could I have the next figure? The supplemental figure, the way of doing it is a method that we have proved works. Was released, the discovery was released last year. And what we have here is a planetary system with 3 planets. They orbit the same star, they transit, and when these 2 inner planets, which are fairly close together, go by each other, they cause changes in the orbital period. And by seeing when the transit occurs, and that's moving back and forth, we can deduce from the transit timing changes the mass of these objects. We don't need radial velocity for this measurement. Radial velocity is always helpful, but in this case, we can get at the masses very well by simply watching these changes. And that means we ought to be able, for at least for some of the Earth-sized planets, to get at their masses, even if we can't get at them with radial velocity. But what you need is multi-planet systems. They are the most valuable thing that we can find. And in fact, we now see in the data that we released 170 stars that have these multi-planet system, candidate systems. Sometimes with 2, sometimes with 3, sometimes with 4, as many as 6 transiting candidates around these. And that's going to be enormously helpful because not only can we get at masses, but we're studying systems of planets like the solar system, not just individual planets. So a great deal of progress and a great deal of encouragement to detect so many of these. Next figure, please. This is a summary, of course, of what we have found. To be explicit, we have released the data to the public at the Space Telescope Science Institute as to everyone who would like to use it or get at it. The data for 155,000 stars, 1,035 candidates with each of the transits, and their properties of each of the stars. We see 68 Earth-size, 288 super-Earth-size. We're seeing 662 Neptune-size, 165 Jupiter-size, 54 candidates in the habitable zones of their stars, and then 170 stars with these multiple candidate systems. So Kepler is making good progress toward its goals. Could I have the animation, please? This is the field of view of Kepler on the sky. That 50 represents about the 50 candidates in the habitable zone. There's Cygnus the Swan, and you can imagine that we found 1,200 candidates in the single field of view. Imagine that we had that field of view covering the sky. Kepler looks at a 400th of the sky. If we had 400 these fields of view, we would see 400 times that number of candidates. We would see 400,000 candidates. And what that's telling you is the stars around us, that surround us, have a huge number of planets and candidates for us to look at. And if we find that Earths are common, Earth-sized planets are common in the habitable zone of stars, it's very likely that means life is common around these stars. And in fact, Kepler is the first step, or is a step in that mankind's exploration of the surrounding galaxy to find life and the extent of life in our galaxy. And Jack is going to tell us about these very valuable systems of stars and that help us understand where the Earths are. Jack?
Well, thank you, Bill. So Bill mentioned towards the end of his talk Kepler 9, which is a system with 3 confirmed transiting planets. It is the only star known to have more than one transiting planet before today. And transiting planets are very, very valuable because that's the way we can get the sizes of the planets. And all the other 100 transiting confirmed planets prior to today were orbiting 1 per star. Kepler 9 had 3. Now, if we can have my first slide, this emphasizes the 170 candidate multiple planet systems that Kepler has identified. The small dots are the stars with one candidate. The small blue circles, and there are over 100 of them, are the targets with two planetary candidates. The red triangles, 45 of them, or excuse me, the 135 red triangles represent the 45 targets with 3 transiting candidates. The 32 pink squares represent the candidates around the 8 targets that have 4 candidates. So we've got a lot of stars with 2, 3, and even 4 candidates. If you look over towards the lower left, you'll see 5 pentagons. They represent the 5 candidates around one star which has 5 transiting planet candidates. But towards the center and a little off to the right in the figure, representing mid-sized planets at medium to long periods among our sample, that stand out, those green hexagons. The only target that we see 6 signals, and those are no longer just candidates. We have confirmed that all 6 of them are indeed planets orbiting the same star, which we've named Kepler 11. Now, in the next slide, this just shows the position of Kepler 11. This is a sun-like star. It's in the constellation Cygnus. It's approximately 2,000 light years from Earth, so the light that Kepler is seeing from this star left the star around the time Caesar was making his conquests. Now, if we can have the video, this is a Kepler view of the system to begin. We see this target dimming like clockwork, but like a very special clock, one with 6 hands moving at 6 different rates. And we interpret this as 6 planets orbiting very near the same plane. Now looking at it face on, and these are very close in, especially the inner 5, very close to one another, the most compact system of planets ever discovered by any technique anywhere. So if I can have the next slide, we see these planets on the occasions when they transit the star. Most of the time, none are transiting. Sometimes 1 is transiting, occasionally 2, and one time, last summer, we observed the signature of 3 planets transiting at the same time, which is illustrated in this graphic. Now, I've said that this is a very, very flat planetary system, and it doesn't look so flat in this graphic. But that's because the planet orbits are much, much bigger than the size of the star itself. So although they're not exactly in the same plane, when they go in front of the star, they look very similar to in the same plane. And in fact, if we had a scale model of just the inner 5 closely spaced planets around this star, it would be as flat as a compact disk. Now, the 6th planet is orbiting significantly farther out. So if we had a scale model that included the 6 planets, I had to go into the attic to find this. it would be like one of these old vinyl records. So let's move on to the next slide, please. And this shows the Kepler-11 system at the same scale as the inner part of our own solar system. So the 5 inner planets, the ones that are closely spaced to one another, are all closer to the star than any planet is to our sun. This despite the fact that these planets are, well, they're not huge, they're not Jupiter size, but they're not tiny either. They range in size from about twice the radius of the Earth to a bit over 4 times the radius of the Earth. And then that 6th planet, it's a little farther out, but if it were placed in our own solar system, it would be between the orbits of the 2 innermost planets, Mercury and Venus. Well, I've been talking about this as a system, and it is an amazing system. These planets are close in. We never thought we'd see this many planets that aren't real tiny, this close to one another. And the fact that they're close to one another means that they're tugging on each other's orbits. And we use the same technique that we use to measure the masses of 2 of the planets around Kepler-9 to measure the masses of 5, these 5 inner planets in the Kepler-11 system. And if I could have my next slide. This diagram is a little more complicated, but it's really important. So what we have here on the vertical axis is the size of the planet, and on the horizontal axis, the mass. We've observed the size by the amount of dimming that each planet causes when it transits in front of its star. We measured the masses, we've weighed, in other words, the inner 5 bodies by the amount that they tug on one another's orbit, retarding or advancing the transit times of each other by 10 or 20 minutes relative to their orbital periods, which are between 10 and 47 days. Now, we estimate the planetary radii, and we're not exact. Really, we're not exact because we know the radius relative to the star very well, but we have a little uncertainty in the radius of the star. In terms of the masses of the planets, we have an estimate by the amount they tug, but these are very small variations, so there's a bit of an uncertainty. So these ellipses for the extrasolar planets, both the 5 that around Kepler-11 that are labeled, that are in blue and labeled by the letters which designate the particular planets, and the 3 around other stars, which are ellipses of a different color, have some uncertainty, cover a different range, but they still constrain both the mass and the size of these stars, and planets, excuse me, mass and size of the planets. We compare them to 4 of the planets most like them in our solar system, Venus and Earth on the small side, and Uranus and Neptune on the large side. These are an intermediate class of planets. And of these 8 that we have, that we know in this range, 5 are around the star that we call Kepler-11. They're the ones we're announcing today. And that little red one is, in the bottom, is Kepler-10 that we announced last month and Bill mentioned as a rocky planet. Now, the ones that we found in Kepler-11 that we're announcing today, they're all higher up on this graph than that rocky planet. The rocky planet is really, really, really close to its star and really hot. These planets are kind of close to their star, and they're warm, but not nearly as hot. And we find that these are bigger for the same amount of mass, which means they must be made of lighter material. They're not super Earths. They're not big rocks. The innermost two, C and B, they might be mixtures of rock and water, or they might be mixtures of rock, water, and gas, or even just rock and gas. But we know the three more distant of this fivesome, called D, E, and F on this graph, are so big for their mass that a substantial fraction of their volume must be made of the two lightest elements, hydrogen and helium gases. So not only is Kepler-11 telling us about planetary systems of a type that we had no idea existed, but right now it's providing our best clues on the compositions of these planets as individual worlds. So if we can move on to my next slide, this is the family portrait. And we see the cousins that were found previously, and Bill showed you in his earlier slide, on the top two row, and the new set of 6 siblings in the family, the long-lost cousins that we found today and are announcing today around Kepler-11 in the bottom row. So if we can go to the next slide, I want to wrap up. Kepler-11 is a surprisingly flat and compact system of 6 transiting planets. The 5 inner planets are especially close together, something that we didn't think would happen for worlds of this size, and really forces us to go back and look at formation models of planets. And it also means that the planets are perturbing one another significantly enough that we can weigh the planets. We find out that they're low density, they're fluffy, they're sort of like marshmallows, but they're not all gas. They got to have something a little heavier there, so maybe a marshmallow with a little hard candy at the core. Now, we really were just amazed at this gift that Nature, not the magazine, but with a capital N, has given us. And with 6 transiting planets, 5 so close to their star, and getting the sizes and masses of these 5 fairly small worlds, there's only one word that I can think of that adequately describes the new finding we're announcing today. The Kepler-11 system of 6 transiting planets is supercalifragilisticexpialidocious. And with that, I'll hand things over to Deborah, who'll give you the outside expert's view on what we've been announcing today.
Thank you. Well, folks, this, of course, is an amazing era of discovery for astronomy, but for exoplanets in particular. And there's no doubt that the search for planets is motivated by a search for life. Humans are interested in whether or not life evolves on other planets. We'd especially like to find communicating technological life. And we look around our own solar system and we see that of all the planets, there's only one that's inhabited. And so naturally we think that finding another Earth-like planet is, identifying a site that's at least friendly here for the evolution of life. So the primary goal of Kepler mission was to statistically assess the occurrence of these small terrestrial worlds. And I remember in March of 2009, when I was here, right after the Kepler mission launched, and I remember commenting that the planets would begin to roll out of the Kepler mission like an assembly line. And that in the first year, we could expect to see Jovian-mass planets or Jovian-sized planets. And after 2 or 3 years, we'd see the Neptunes begin to roll out, and then finally the Earths. So I'm amazed to sit here today and see that Kepler is actually reaching the milestone discoveries faster, certainly, than I anticipated. Kepler has blown the lid off of everything that we know about extrasolar planets. And this week, to me, feels very different than last week did. And I'll tell you, summarize, actually, the 3 reasons that I say that. So first of all, from the Doppler planet searches, we could see that the gas giant planets like Jupiter were less common than the low-mass planets. We could see a mountainous sort of rise towards smaller and smaller or lower and lower mass planets. But our detection technique was hitting a wall just because of the precision of our measurements. And so we were at the point we were pounding away right now on this wall, trying to shake out a few planets that are, 2, 3, 4, 5 times the mass of the Earth, the super Earth regime. But our statistics there are not so good. And so what Kepler has done is it's extended a bridge that crosses this gap in our knowledge of what kind of small planets form. Still, the amazing thing to remember is that the detection of large planets or massive planets is always going to be easier than the detection of the small guys. And so what that means is that the statistics that Kepler has gained, even on the exoplanet candidates, okay, maybe 20% of the candidates won't pan out. But statistically, we can see that we understand the fraction, the rate of occurrence of the massive planets. From Jupiter, I think, all the way down to Neptune, actually. Those numbers are solid. We can take those numbers to the bank. That's pretty amazing. It's impressive, right, that the number of small planets is growing in a region of parameter space that theoreticians actually predicted might be a planet desert. The second amazing thing is that it's really difficult to untangle the signals from multiple planet systems. So it's worth reemphasizing that Kepler now shows that something like almost 1 in 5 of their stars with transiting planets hosts at least one other planet. And Kepler 11, which was just presented by Jack Lissauer today, is an absolutely staggering result. With 5 low-mass planets in the system, this discovery is as momentous as 51 Peg was in 1995. It shows that planetary systems with several small planets like our own seem to be common. And then the third point is that Kepler's really reaching out into a different part of the Milky Way galaxy than we're observing with the Doppler technique, our own nearby neighborhood. And I think it shows us that the adjacent neighborhoods in the galaxy look a lot like our own neighborhood. And so I think that's encouraging and important if we're trying to make extrapolations about the formation of planets elsewhere and perhaps life. So I can also actually provide some insight about the enthusiasm of the public for the Kepler data. At Yale University, we were so excited when we saw the Kepler light curves that we teamed up with the Citizen Science Alliance, who host Milky Way Galaxy Zoo, among other Zooniverse projects, to let the public participate in discovering planets at planethunters.org. When we started the project, we discussed it among ourselves, and we really thought there was about a 50-50 chance that this project would completely flop because, Galaxy Zoo shows beautiful pictures that people get to look at. We're showing time series brightness measurements of stars. But in just a few short weeks, we have over 16,000 dedicated users, and they send their greetings to us from Turkey, Russia, Poland, Spain, the Canary Islands, Italy, Brazil, Argentina, Chile, one country after another. It's amazing. The users have made more than 1.3 million classifications just using the first release of 35 days of public release data. They've identified hundreds of solid transiting planet candidates and eclipsing binary systems that weren't published before. So, of course, they're very eager now to see the list that will be coming out and see if they have any matches. We're really excited and appreciative that 12 hours ago, NASA and the Kepler mission has poured, essentially quadrupled the amount of public release data into the archive on an accelerated schedule. This is really wonderful. At planethunters.org, we hear from teachers who are using Kepler data through the Planet Hunter interface in their school curriculum, from students who are having fun searching for this needle in a haystack, just because they know the payoff is going to be so enormous. I had one of the Planet Hunters email me yesterday, and he or she said, that they had found 4 transiting planets, and they felt so proud. And another person commented that they were going back to school now, that they'd seen the data and they wanted to learn more and they were returning to school. But really the dominant recurring theme that we hear from the public is that they're excited because they get to contribute to real research and they have a sense that they're a part of history. They understand the importance of the Kepler data. And I want to just echo that and say that also I feel this is an incredible historic moment and just want to thank the entire Kepler team for this treasure chest of data that they provided. So back to Trent.
Thanks very much, Deborah. Okay, let's jump into the question and answer session. Just a reminder for everyone in the audience to please just wait until we get a microphone to you. There should be 2 running on either side. And please identify yourself and your media affiliation before you ask your question. For everyone online, please try to direct your question at least to a panelist to help avoid some confusion. And for those joining by phone, you can signal the operator that you have a question by pushing the *1 keys on your telephone. And I understand we have one question here in the audience. So
yes, Randy Shostak, reporter with EOS, the newspaper of the American Geophysical Union. Fantastic results. I wonder if panelists can comment on how these results might influence the emerging research efforts. For instance, change what researchers are looking for, how Kepler is used, etc.
I'd be happy to answer that one. Basically, one of the things that we are doing is determining these frequencies. How many, around how many stars, what type of stars, because there will be follow-on missions. And follow-on missions need this kind of information for their design. There are a couple of designs out there. One is a coronagraphic kind of approach. Another one is big interferometer. And they have different areas of application. And so one of the things that we're doing in some sense is providing the information required for the future missions that will go out and find the planets nearest and the nearest stars, as well as going out and finding the composition of the atmospheres of these planets. And that is another step toward our exploration of the galaxy.
let me just do a quick check for, looks like we have one more here.
Hello, I'm Paul Workman with Canadian Television. A general question, first of all, how much does this bring us closer to discovering whether there's alien life? And second, how do you now find out if the 5 planets in the habitable zone do have life?
Patience. That's how it's done. And lots of money. That's reality. This mission is designed to do something and do it as well as can be for this first step. It finds the frequency of these objects, these planets, and their distribution. But you must do the other steps. You must, in some sense, build the cathedral. The first generation is going to build the foundation. The next generation is going to build the walls. Third generation is going to put the ceiling on. The fourth generation is going to enjoy it. And so we are, in some sense, the first generation. We're finding them. The second generation is going to build instruments of far more complexity than what we have to go and find these nearby ones. And even greater demands are going to be made to find the atmospheres on these planets. And then, of course, having done that, our grandchildren will have to decide what's the next step. Do they want to go there? Send a robotic system there? So this is only one step. It's an important step, but there are other steps that must follow.
Great. I'd like to go to the phones now, if we're ready. I believe Seth Bornstein from the Associated Press is on. So, Seth, go ahead.
Yes, thank you for doing this. This is more for Bill. Of the 54 in the candidates in the habitable zone, I think you said one was Earth size, or actually smaller than the Earth, and 4 were super Earths. Does that mean essentially that the other 49 are more candidates, as you say, for for satellites, for moons, or is there a group that is sort of in the range that might be rocky? And the other question is, what I know definitions for habitable zones vary. What is your temperature definition? Is it 0 to 100 C, or is it slightly bigger? Thank you.
Yes, Seth. The temperature range that we consider part of the habitable zone is extended, in that clearly if you extend it down below the freezing point of water, that's what we calculate if the planet has no atmosphere. If the planet does have an atmosphere, the temperature is certainly going to be warmer than that. It may be very well to have liquid on its surface. The habitable zone is a very fuzzy concept. Certainly Enceladus and other moons that are very far out, but are heated by the internal energy of their moons. There's possibilities of life there as well. We're just trying to pick a region that has a higher probability of having life, sort of a start in this search. Did that answer your question? And you asked about the other ones as well. We have these 5 that are small, 9/10 the size of the Earth, up to twice the size of the Earth. A group that are Neptune size, and a small number of the order of half a dozen or a dozen that are Jupiter size. And clearly all of those are interesting to us. We will want to explore them further, but we don't know much more about them than we've told you at this point. We have a lot of work to do to better understand them and to confirm them.
Okay, let's go back to the phones, this time with David Perlman from the San Francisco Chronicle. Go ahead, David.
Yeah, thank you very much. I have a question for Bill, I guess, and that is, how do you define a candidate, and when does a candidate not be a candidate anymore, but be something confirmed?
That's a very good, tough question. In that, of course, when we see a series of transits, the first thing you'd like to say is, oh, that's a planet. More than likely, it's going to an eclipsing binary, or maybe some galactic cosmic rays that hit your detector, or a lot of other phenomena. One of the ones that we are the most troublesome with are the eclipsing binary stars. When we look out in the galaxy, we see not just our target, but lots of stars in the background, lots of these little red M dwarfs that are everywhere. And if they're an eclipsing binary, the instrument thinks it's seeing the target star vary. So we go through a great deal of effort for each of these objects that look interesting. Our analysis pipeline provides a beautiful example of all the threshold crossing events that have a big enough signal to be interesting. It looks at these, and the pipeline looks at these and asks, is there a secondary eclipse? That's a warning right away that this is a star. It looks at the shape, and if it's V-shaped, it's a warning right away this is probably an eclipsing binary. So the analysis pipeline that our team has put together has built a system that eliminates most of these false positive events. And some of the tests, some of the work they've done is absolutely elegant. Nevertheless, after they've processed the data for 4 months, it comes to the science team, basically of observers and others, and we look at these and ask, which of these can we go to the telescope with and have a chance of proving they're a planet? We look with the ground-based telescopes and ask, are there other stars really close in that could explain this? We look at, we do reconnaissance spectra with our observers to see what the characteristics of the star are. If you don't know the size of the star, you don't know the size of the planet. So we make an effort to get at the size of the star through reconnaissance spectra. And then if it still looks good, we want to confirm it. We go to the biggest telescopes in the world, the Keck's and the HETs and the Nordic optical telescopes, and go and measure the radial velocity fluctuations. So it's a series of steps that generally takes from when the data comes down from the spacecraft to when we have an announcement, generally of the order of a year. That's the kind of time that's required to be able to prove something is a planet.
You know, I'd just like to jump in and say, you know, you listen to Bill's description there, and it should give you a better understanding of the fact of just how much work goes into dubbing something, taking something from exoplanet candidate to exoplanet. Everybody wants to be able to, you know, just go through and roll out hundreds of planets, but each and every one of these require this sort of painstaking work to go through and confirm that they actually are planets and not something out there trying to trick us into thinking it's a planet. So I mean, Bill gave a good description there, and you should kind of think about that, because it's an amazing amount of work by a lot of people that's going into this.
And I'd just like to add, Bill did an excellent description, and all the steps before the last we're basically doing for every candidate before we'd even consider calling it a planet. But there are 3 different last steps, because those radial velocities Bill mentioned, the Doppler method, that works for big enough planets orbiting close enough in around bright enough stars. But for Kepler 11, they're too small, they're not super close in, and they're around a fairly faint star. And so the second method is one that's only been used twice, for Kepler 9 and Kepler 11. And that's, as Bill mentioned in his talk, the transit timing variations to see the tug that they're exerting on one another. And you can't have that in triple star systems because they would go unstable. The stars are much more massive. So that's the second way, which, like the radial velocity method, also gives you the mass. But it's only on systems where the planets are big enough or close enough that it's possible. So the third method, which we've just used on a couple of objects, one, the third planet around Kepler 9, and one, the 6th planet around Kepler 11, is to look painstakingly at the field right around the star and characterize the star as much as we can, and look at the details of the shape of the planet and show that the shape and the details of it just don't make sense for any false positive model with any reasonable chance of occurring. And therefore, we're more than 99% certain it's a planet, and we call it a planet. And that's better than the rates of things that have been called planets in the past, so we think that's pretty good. But if it's not at 99%, at least, it's still just a candidate.
Anything else to add? Okay. I know we have one more question, at least on the phone. Let me take that, and then we'll come back to the audience and just do a quick check to see if there are any further. Kelly Beatty, Sky and Telescope. Go ahead.
Thank you very much. Jack, in concluding that some of these have atmospheres, you, as I understand you've basically been working on a model fit to their densities. When you measure these transits and the transit times, if there are atmospheres around them, how do the atmospheres affect the diameters that you derive? Do the atmospheres cause you to come up with a diameter that's artificially larger than the planet itself?
Well, you have a good question. And what is the size of the planet? For Earth, you generally consider the size of the solid surface, because then the atmosphere is just so much more tenuous. But for giant planets in our solar system, we have to say, what is the size where we want to cut things off? And we have to say that for these planets too. And it turns out that the size at which the altitude, the density in the atmosphere that causes a transit is a little bit less dense, so a little bit higher, So get a little larger than what we would call the measurements of the sizes of, say, Jupiter, Saturn, Uranus, or Neptune. But it's by less than 1% in those cases. It may be a little more in these cases, but it's a pretty small difference.
Great. Let me just do a quick check in the audience, see if there are any further questions. Okay, we'll go to the phone line. We have Nell Greenfield-Boyce from NPR. Go ahead. One more time, do we have Nell on the line? Okay, I think, let me just do one more check, see if there are any further questions. All right, so I know we have a question from Ames Research Center. Let's go there. Go ahead, Ames.
Okay, hello. Jens Ergon, Swedish National Television. Could you please elaborate a bit more on these 5 almost Earth-sized planets in the habitable zone? I mean, what could you tell? I mean, what kind of stars do they circle? How far away are they? What might they look like? And furthermore, I mean, if you wouldn't characterize these like Earth-like planets, I mean, what is the definition for an Earth-like planet then? And when might these Earth-like planets pop up? Would they exist?
That's a very, very hard question. We can measure these. We can detect them. We have yet to prove they are a planet. Many of these are small, so we haven't confirmed any. But it's certainly going to be something we will investigate in the coming months and years. But at this point, I can't tell you much about them, other than generally the stars they orbit are stars quite a bit smaller than the sun. Of the order sometimes half the size of the sun. The temperatures are very much lower. The sun is about 5,800 Kelvin. These stars are almost half that temperature, of the order of 3,000, 3,500. I think some of the slightly bigger objects are around stars, again, cooler than the sun, but the temperatures, I think, run about 4,400 to 4,800 Kelvin, so they would be considered K-dwarfs, stars intermediate between these very small, cool stars and the hotter star like the sun. But we don't know much more about them as yet. We have discovered them, of course, only very, very recently. It takes a great deal of work to find them, to make sure that we understand a little bit about the star themselves. It's difficult often just to get the information on the star. How big is it? What is its composition? So the reconnaissance spectra and the interpretation of the reconnaissance spectra, the understanding of how old the stars might be, which tells you a little bit about how mass and size vary for these stars, are things that we still have a lot of work to do. So I'm afraid I can't give you much information other than many of them are around the cooler stars, stars smaller than the sun.
Just to add a couple things, if they are planets and they are in the habitable zone, then the star that they see in the sky close up is a lot redder than our sun. And as Doug and Bill stated earlier, the reason the habitable planet, small habitable planet candidates we're seeing now are only around these small faint stars is we just haven't had enough time. We are searching for planets that are true Earth analogs, Earth size, around stars like the sun, but that's going to take a few more years of data to find them.
Okay, let's go back to Ames. We have another question. Go ahead.
It's Mike Meacham with Aviation Week. You've had 4 months of recorded observations out of, I think it's a 3-year mission, so you're really just getting started here. I'm trying to get an idea of the results you expect. Do you expect that they could be linear in the sense of you've got 1,235 candidate planets now, or will your early observations have you started to see enough of the candidates that now you're getting into the fine grain detail, and we won't see results stepping forward as great as these have been?
That's right. I mentioned in my talk that as you go further and further out to larger orbital distances, larger orbital periods, the chance of getting an alignment falls dramatically. So we see this huge number of candidates in the first 4 months of data. But if we look at the following years, we don't expect to see anywhere near that kind of increase. What we will see is fewer but more interesting planets. They'll be the ones that are further out, that are cooler. The other aspect that's happening here that is that as we go on, the analysis that we do to correct for the stars are very noisy. The stars are noisier than we expected. So it's harder to find these small signals. And we have a group of people at NASA Ames that work very hard to correct out the noise and the glitches and things like that in the data. And as they do so, the analysis pipeline becomes more and more capable of finding these smaller objects. So we're going to find in the years that are going on that we're able to find, even in the data that we're releasing right now, more planets, but they'll be smaller planets to be buried in the noise. And so it's the capability of our mathematical analysis that allows us to find these small objects, but we do not expect to see the kind of plethora increase that we see now. There will be many fewer as the years go on.
So quality is coming up, not quantity.
Okay, let's go back to the phones. Let's try Nell Greenfield-Boyce at NPR again. Go ahead, Nell.
Hi, can you hear me this time?
Yes, we can.
Okay, sorry about that glitch before. Thanks for doing this, and thanks for taking my question. Do you all anticipate that the first confirmed Earth-sized planet in a habitable zone will be one of these candidates? I mean, do you feel that the Holy Grail, as was said before, is actually in these data waiting to be confirmed? And I know you talked about some of the steps that are required for confirmation, but just to reiterate, how long do you think that confirmation will take?
Well, I guess I can speak to that. Again, no, I wouldn't expect the Holy Grail, if to use the term that I used, to be in this set, because again, the Holy Grail, an Earth-sized planet, are in the habitable zone around a sun-like star. Obviously, the orbital period of that would be about a year. So, in fact, you would only, if you were far away in the plane of the Earth's orbit looking at transits across the sun, you would only see a transit by that planet once every year. So, in fact, it would take you 3 years, well, first off, it would take you 2 years before you even saw a second blip that, sort of stood out in the middle of nowhere, a year after the first one came along. And it would be a third before you came along and said, wow, we seem to be getting this blip every year in that period. So, in fact, at this point, with only a year and a half worth of data, we wouldn't have enough blips yet to identify it as a recurring event. So in that instance, no, I would say just on that standpoint, the planet candidate that could be our Earth-like planet, if you will, or the Earth-sized planet in the habitable zone, to be more precise, wouldn't have emerged from the data yet.
Okay, we have Alan Boyle from MSNBC on the phone. Go ahead, Alan.
Hi. With the earlier data release, there were some candidates that were held back for confirmation by the Kepler team, 400. I wondered if there are a number of candidates that are being held back this time for similar reasons.
No.
No, they're not. All the data, in addition to the 400 targets that the team had extended exclusive use period so that they could have a full season of follow-up observations, were released actually just a few hours before all of the data on the 156,000 for the second 3 months of the mission. So all the data is out there. There are no targets that have been held back at this point.
And one of the things I think that we had an opportunity to do was to take a look at those candidates that were held back during the summer and do reconnaissance spectra of many of those, of the thousands, the 1,200 candidates. And we found that some of those that we had released, some of those that we had reserved were in fact false positives, things that ultimately were eclipsing binaries or whatever. So the groups that we have released, that is all that we have released now, are much more heavily vetted. So we have a much better understanding that these are really good candidates. Go out, observe these, and you're going to find planets. And we have released all the data for this 4 months. We of course have data after that period of time, but we don't have any candidates that we can show you.
Okay, let's move on to Mike Wall of Space.com. Go ahead, Mike.
Oh yeah, so I saw in the like a little press, the press release that actually Kepler went into safe mode, and I was just wondering if you guys could just speak to what the problem was and if it's serious or if everything is going to be okay going forward with the telescope.
Yes, in fact, the Kepler spacecraft did turn up in safe mode at the normal contact, and the team is currently working the issue. It appears to be, at this point, and this is preliminary information, it appears to be a fault with one of the star trackers, which is something that we have experienced before. The data shows that the spacecraft is in fine shape. In fact, it's been brought out of safe mode and is in standby mode. And probably even as we speak here, they're doing a full download of the mission data recorder so they can make sure that they know what's going on and find a see if we can design a way to avoid this problem in the future. But this does appear to be a fault that we have experienced before, and we do not believe it represents any serious threat to the mission.
Thanks. Let's go back to Seth Bornstein, the Associated Press. Go ahead, Seth.
Yes, thanks. I want to, if we could focus in on the smallest of planets. First, what is the smallest size you saw? And looking at the one Earth-sized candidate in the potentially habitable zone, I believe that's a 0.6 Earth radii and radius. And I'm wondering if how secure are you about that? I mean, and would, because it's so small, would that eliminate using radial velocity to get it? And I'm wondering, overall, how many planets have you found that are actually smaller than Earth? Thank you.
Maybe Deborah can talk about confirming these small objects with radial velocity. She's been working on a new system that may represent a significant step forward in the ability of radial velocity systems to look at smaller objects.
Well, I can certainly comment that this is extraordinarily difficult, that the detection, our measurement errors right now are about 1 meter per second, and to find an Earth analog, we would need to be able to measure an amplitude of reflex velocity in the star of 10 centimeters per second. So that means we've got to shrink our 1 meter per second error bars by a factor of 10. And yeah, we're investigating. I mean, we have at Yale a Doppler diagnostic facility where we're setting radial velocity precision as the figure of merit and really trying to hammer down on all of the error sources that we can think of. But I think we're ways away. Maybe the best strategy we have right now is if our errors are random, that's a big if, and not systematic errors, then one way we can shrink the error bar is by taking many observations. So you take one measurement, you get 1 meter per second, you take 100, you reduce that precision or improve that precision by the square root of the number of observations. So that's how you can get from 1 down to 10. Problem is that it doesn't really go down that fast because our errors really aren't completely Gaussian or completely normally distributed. So it's the focus of work. And I think like everything in this field, we have to go stepwise, one step at a time. And it's too bad we can't just sort of leap to the end and see the answers. But we're all doing the hard groundwork right now to try and make that happen.
And I'd like to add that if we get lucky and we find some Earth-sized candidates in the habitable zone of stars with more than one candidate. And if the spacecraft is healthy, stays healthy, funding stays healthy, and we can have an extended mission, maybe we'll be able to observe long enough that we'll be able to see transit timing variations that one planet causes on the other and confirm it that way, even if radial velocity confirmation is impossible for such a small planet.
Okay, we're going to take the last question. This is back to David Perlman with the San Francisco Chronicle. Go ahead, David.
Yeah, thanks very much. I have to try to follow up before. Bill, I'm still not clear as to how you define what is the definition of a candidate. I understand how you confirm it, and you all were very helpful on that subject. But how do you actually define a candidate that makes you then go and attempt to confirm it?
Okay, that's let's talk about that for a moment. We have this analysis pipeline. It goes through the data in an automated fashion, and it finds any set of transits that have a signal-noise ratio like 7. The probability of getting something like that at random data is 1 in 100 billion. So you see that and you say, well, here, the pipeline produces it. It gives you a list of these things. This star has such and such events, threshold crossing events, with this period, this amplitude, and it makes some checks, and it then spits this out, gives us a report, and the team that was called TCERT, the Threshold Crossing Events team, looks at the results of this computer output and then begins to think about it themselves. Do they believe this? Do they really think this is a candidate? Is the threshold crossing event a candidate? If the team looks at it and says yes, it becomes a candidate because they say it's a candidate. They make that decision. A group of about 8 or 10 people meet generally once a week to make that decision. And it's that group then that puts a priority rank on these things and sends it to the group of people, what's called a follow-on observing program group, FOP, who look at what's been given to them and see, here is what TCERT wants us to look at. And they look and they decide from the available telescopes, the instruments, and so on, which of these is the most practical to do. And then that, again, that's still a candidate, and they go forward with the validation procedures that we talked about. But the conversion of a threshold crossing event to a candidate is done by team members meeting in a group once a week who make that decision by looking at the data.
And then, so Bill has described how something becomes a candidate, and it stays a candidate until either it's confirmed as a planet or we show that it's a false positive.
Right. Yes.
Okay, with that, we'll end today's media conference. Just as a reminder, you can find out more information about today's announcements and keep up with the latest on the hunt for planets at www.nasa.gov/Kepler. I'd like to thank the panelists for their time today and thank all of you for joining us. Have a great day.